Okay, let's go from current slide. All right, before we launch into that, let me just make these couple of announcements. The math team, Ms. Gerasi, is meeting with the math team every Friday at 12 noon and every Monday at 3 in the afternoon in C100 on the Birmingham West Campus, and they're having a good time. And if that's inconvenient, either of those times are inconvenience for you, and you want to have practices out here, I'll meet with you anytime during my office hours. Hopefully, I will be over some of these treatments in a bit. I'm supposed to have one tomorrow, but they said don't have it until they get the blood work in. I don't think they're going to give it to me because I don't think they would have last week if they looked at blood work first. So I'm pretty sure. So hopefully next week I'll have more energy than this week. But anyway, if you can participate, I think you'll find it, number one, a lot of fun, and number two, very helpful in math, okay, because you'll be doing stuff that you wouldn't have otherwise, or get ahead of yourself, okay. We have a training thing coming up next Thursday afternoon from 2 to 3:45, sorry, 2 to 3:45, next Thursday afternoon, 1 week from today, down in room 209 in this building. So unless the thing fills up, I'll probably be down there for the training. So don't look for me then. But while I'm on that subject, let me talk a little bit about my office hours now. As you might can tell, I'm really dragging today. I mean, I almost had to force myself out of bed this morning. I was so exhausted. And I have a feeling that shortly after noon today, once I get everything done I need to do today, I'm going home and going to bed. So I probably won't be in my office all afternoon. I'll be here for a while after class, 10:45. I'll probably go in, since I brought my lunch in this morning, I'll go in and eat here while I'm doing other things. And then I'll try to take care of all the things that have to be taken care of today, and then I'll probably go home. Tomorrow, normally I have office hours on the Birmingham campus, so I haven't recently because of the treatments. But like I said, I'm scheduled for a treatment tomorrow, but I don't think it's going to happen. But I have to be there for blood work at 6:30, and it usually takes them at least an hour to get the results back. But then it has to go to my doctor, and I doubt if he's going to be in before 8. But whenever he sees it, then he'll determine whether I have the treatment tomorrow or not. So I'm guessing I may not know the answer to that until around 8:30 or so, giving them time to get there and get the response and things like that. 8:15, 8:30, something like that. I'm hoping to know. And then if I don't have treatment, I'll be heading to the Birmingham campus. So, but I probably won't get there before 9 o'clock, and it may actually be after 9. But that's just a guess. If I do have treatment, then I won't be there at all. So, things are just kind of up in the air there. And hopefully next week I'll be back on a normal schedule. I hope anyway. They had scheduled these treatments for be 3 weeks in a row. I've had 2. I don't think we'll have to do this time. Then they were going to be every other week. I doubt if that's going to continue. Then they'll go to every month. I'm guessing at some point we'll go to every month. But I don't know. I'm not the doctor, so I can't decide that. That would be if he gives me any input on it, I think that's going to be perfectly adequate, and I don't think I should have any treatments until things bounce back. Okay, but I guess he'll make the call, but I'm going to argue my case fairly, I hope, reasonably. Okay. Now, a couple of other things. I've seen the announcements, but I haven't been near a printer to print them when I've seen them, but I have seen some on the wall. I know homecoming's coming up sometime really soon, so it sounds like lots of fun activities going on around that, so watch for the notices and take advantage of those. All right, any questions on anything we've done so far? Okay. We were on example 7. Okay. And we had pretty much finished 7A. This is on page 303. All right. Now, no questions? We did it one way, the book did it another way. I'm going to do from my memory, and you correct me places I'm wrong. Our way, we got y is equal to 5.6 times the sine of, well, again, I like to pull out the b, isolate the b, and if my memory's right, that was pi 6, wasn't it? Okay, pi 6 times t minus, I wrote in a parentheses and wrote t, and the t parentheses disappeared. I don't know what's going on here. Minus 1, I believe it was, wasn't it? Plus 5.7. All right. Theirs, they came out with that. Okay? So, I hope somebody brought a calculator today, because the B part of the problem says, there it is. Find the depths, and this was depth, the Y was the depth, at 9 a.m. and 3 p.m. Okay, and if remembering back, T was the time after midnight. So 9 a.m. would be T equal 9. Okay, so we're looking for Y is equal to 5.6 times the sine of, let's see, let me do this because I think otherwise it might be a little more confusing. Sine of pi 6, and if you put 9 minus 1, that would be 8, right? Okay, plus 5.7. And since I can just look at this and say 2 will go in that 3 times, 2 will go in that 4 times. So actually what I would put in the calculator is 5.6 times the sine of, now what mode should we be in? Radian mode. 4/3 pi plus 5.7. Okay? So that's what I would plug in the calculator. Now, it depends on what kind of calculator you have. Most of you probably have pretty modern, neat ones that you can just do it as you read it. 5.6 times the sine. You don't even have to put times, I think, most of them anymore. Sine, and as soon as you put sine, it'll open a parentheses for you. And then I would be 4 times pi, or actually, most calculator, you can just put 4 pi divided by 3, then close, be sure you're in radian mode first, okay? Close your parentheses, and then add 5.7, and you should get an answer. 0.850, is that what you said? Yes. 0.850. For some reason, my pen is not writing well. Okay. Now, if we look up at your table that you had, if you got your book open, between 8 and 9 in the morning, that's between 3.8 and 0.1, that certainly falls in there. So that looks like a very reasonable answer. Now let's do the same thing, but we're going to use it the way the book did it. Okay? And that will be 5.6 times the cosine function, and that opens a parentheses for you, 0.524 times 9 minus 2.094. Okay, that's the way they do it. Okay, so much better to me to factor out that and just have something simple in here. Plus, be sure you close that parentheses. Stay in radian mode. Plus 5.7. What did you get that way? .6 cosine, and and then the open parentheses, 0.524 times 9 minus 2.094, closure parentheses, plus 5.7 equals. What's that?
I don't think I got it right. Because I got it 2
Okay. Let me look on while you're doing that. 5.6. And that is 0.524 times. Okay, wait. Yeah, 9. That's fine. Wait. Okay. Does your book do parentheses as times? It does. Okay. I mean, your calculator. Okay. Minus 2.094. Then close the parentheses. Plus 5.7. Huh?
That's how it worked.
No. What did you have before? See?
Yeah, it worked.
0.83. Yeah. So that gave you 0.83. What? 9. Okay. Why is the pen not writing? This is driving me nuts. 3.9. Okay. Not far off, but not exact. Okay. Now, why the difference? Well, number one, we used an exact number here. 3/4 pi. That's an exact number. Okay. They used a round off here and a round off there. So more than likely, and especially when you have a subtraction of two rounded off numbers, that can increase your error. Okay, it's not a bad error, 0.84. That would be not far off from 0.85, but it's not precise. Okay, as precise. Cosine is just as good as sine, but where they made what introduces the error is the fact that you have your they rounded off the pi 6, and then 2. That multiplying by the pi 6 is, you've actually rounded here, and then the difference was also around. So it can lead to more errors. But it's close enough for government work. Both of those are good answers. So we're going to see how they did it, which means I need to erase what we did. But I like the way y'all did it. Okay. Oh, they went to a new slide anyway. So at 9, it was that. 5.6, that, bop, 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 and they got 0.84. They rounded to 2 feet. Okay. Now, the second part of B was at time 3 o'clock in the afternoon, wasn't it? Okay. Now, what would you have done? Let's do it our way first. Y is equal to 5.6 times the sine of, let's see, pi 6, wasn't it? Yeah. Times, okay, I'm going to put my t in there, t minus 1 plus 5.7. Okay. Now, what time do we put in for t if it's 3 in the afternoon? 15, because it's 15 hours since midnight. You ever mess with military time much? Yeah, same type deal. Okay, so this will be 5.6 times the sine of, now this is going to be 15 minus 1, right? So it'll be a 14 here, and for some reason the pen's not writing. Okay. That would be 3, that would be 7/3. So this would be sine of 7 pi thirds plus 5.7. Okay. Oh, man. Punch that in and see what you get. If you ever notice that, this was pointed out to me when I lived in Nebraska, we Southerners are fairly violent because we punch numbers in. They press numbers up there. Okay. Yeah, no. Okay. No, people look, literally they notice that. Punch 7, you know, in the elevator or something like that. So we press 7. Okay. All right. Jared's here.
10.549.
Okay, let's see. 1025.
10.549.
Okay. Now let's use theirs and see what they got. Y is equal, we're doing the C part of example 7 on page 303. 5.6 cosine of 0.524 times 15 minus 2.094 plus 5.7. Okay, see what you get that way. I'm guessing they don't do 5 digits like we did, but let's see how close we get. 10.56. 565, you said? 567. Okay, so not far off. Okay, again, there is a difference there, and I would almost guarantee it's because of their round-off errors. Okay, now, if you look above, because you're on a period of, remember we said the period was how much? 12 hours. Then a 3 in the afternoon shouldn't be far off from what 3 in the morning was. And sure enough, it was something between 8.7 and 11.3, 10.55, 10.567. Yeah, both of those would be right in that range. So it looks good. Make sense? Let me, sorry, clear all this out of the way so you can see what they did. Then they plugged in 15 for 3 in the afternoon, and they got 10.57. Okay. Now, they also spent one more. Okay, wait. Oh, that was the B part. Sorry, that was all on the B part. The C part. Okay. It says the C part of the problem was a boat needs at least 10 feet of water to moor at the dock. During what times in the afternoon can it safely dock? Okay. Now, let's go back to our formulation, and that would be y is equal to 5.6, was it? Sine of pi 6 times t minus 1 plus 5.7. Okay. Now, they say use a graphing utility, which you can. I've noticed some of you have those. And you can see that, see the graph, and then pick a line and say y equal 10 and find out the times that's going to be true. That's how they show in the book. But I'm going to show you don't have to have a graphing utility to do that. What you can do is we want y equal 10, plug it in and solve for t. Because the question is, at what time will it be? So that's going to be t. So let's do that. This is a little more involved than using a graphing utility. We'll put 10 is equal to 5.6 times the sine of pi 6 times t minus 1 plus 5.7. Okay? Now, first thing I would do, of course, is subtract 5.7 from both sides, right? You are trying to solve for t here, okay? So this would give us 4.3 is equal to 5.6 times the sine of, get out of there, pi 6 times t minus 1. Right? Because those add to 0. Next thing I would do, divide everything on both sides by your 5.6. And for some reason my pen is not writing well, okay? Now, I'll need some of you to actually give me a number there. .3 divided by 5.6. .3 divided by 5.6.
0.767.
76 what? 7. Okay? This thing is driving me nuts. That's equal to the sine, no, don't lose your screen, leave it there, of pi 6 times t minus 1. And my pen is so slow today. And it keeps flashing up. All right, now, we haven't done inverse functions yet, have we? Okay. We're going to really soon, so this won't be anything but just doing it. What it is, we want to undo this. Okay. This represents an angle. The sine of that angle gives us a number. So the inverse sine, and you can find that usually on your calculator, the button's right above, like the shift or second or something like that, function of the sine, you'll see sine to the minus 1. Now that doesn't mean 1 over sine, that means the inverse sine. We'll get there in a second. So what you do is press, you have this on your screen right now, all right? Okay, so just press that inverse sine key. That's either a second function or...
The 7.67.
Yeah, that's on your screen, just press an inverse sine. And what you're doing is then inverse sine of 7.67, 0.67, 767, whatever I'm saying, okay? This pen is equal, and when you do the inverse sine of the sine, they undo each other, okay? And that leaves you just pi 6 times t minus 1. Probably should have put brackets there, okay? Now, that gives you a number. You're in radian mode, right? Okay. So what is that inverse sine of that thing?
0.875.
Okay, approximately. So leave that there. And that is approximately equal to pi 6 times t minus 1. Okay? My pen's just is writing whenever it wants to and quits whenever it wants to. There we go. All right. So what I would do to that, whatever number you have on the screen, okay, multiply it by 6 and divide by pi. Okay. Okay. And whatever that is, that's equal to t minus 1. This thing right here is 1.672. Okay, and then add 1 to it and you get 2.672, right? Is equal to t. All right. Now that's so many hours after midnight. But remember, we're on a 12-hour period, so that would also be 2.672 hours after noon. Okay? Now, if you go back and look at your chart, 2 hours after midnight, that's when you reached about 10 feet. Okay? So then you come back down later, and it goes back to 10 feet. So what we have to do here, okay, is let's figure what time this is in the afternoon. Okay? Well, it's 2 o'clock in the afternoon plus something. So let's take your 0.672 and multiply it by 60. Oh, wait. Yeah, 60 minutes in an hour, right? That is a fraction of an hour. What does that give you? about 40 minutes, 240 or something like that. 0.672 times 60.
40.32.
Second?
40.32.
0.32. Let's just call it 2:40 in the afternoon. Okay? Okay? Now, we already saw from our table that the max was reached at 4 o'clock in the afternoon, right? So, that's, you reach 10 feet an hour and 20 minutes before 4, and then following the curve, that means an hour and 20 minutes after 4, so from 5:20. Does that make sense? So from 2:40 in the afternoon to 5:20. Okay? That's using just calculate, not using a graphing calculator. Okay? And let's see what they got using their graphing calculator. So we just said 2:40 until 5:20 p.m. Okay? So hang on to that. I'm going to erase my screen now. You got it firmly planted in your mind. What they did, they just continued the graph. Now they used the cosine. Ours would look very, very similar to it, maybe a little off, but not much. And it would give you this curve. This is the part they gave you already from midnight to 12 noon. And then this continues until midnight again. So you see this curve looks just like that one, just like we did. And that gave us 14.7. We had 14.6 something another, right? Now, that's at 10. And then what they did was say this was 1.3 hours before your peak at 4, and then another 1.3 hours after that, you get that. So what is 0.7 times 60? 42 minutes, and this would be 18 minutes. So we did 20, yeah. So you see we're right in the same ballpark. Okay? 242, we said 240, until 518, we said 520. You know what? They're not precise enough anyway. I think you get by with that. I would try to get there, say 245 to, and leave by 5:15, because you don't want to get grounded. Okay, so give yourself a little bit of slop there. Okay, so you see how they do it. You don't have to use a graphing calculator. You can do it analytically, which is what we did. But on the graphing calculator, they just put an extra function in here, y is equal to 10, and that showed you in the morning it's thin, in the afternoon it's thin. But we did it just using the formula, and you got it that way too. And a little bit of reasoning. All right, any questions on that? Okay. That ends the section. Let's do vocabulary. And I want to thank you, class. You are really a good participating class. I have a big 112 class earlier in the morning. I felt like a dentist trying to pull teeth to get them to respond. I could hardly get anything out of them, but y'all answer well. Y'all, of course, more advanced. Okay, let's do 4.5 vocabulary. One period of a sine or a cosine function is one blank of the sine or cosine curve. I know what word they're looking for. There's several things you could probably say. Does anyone have a clue what they're looking for? They're looking for the word cycle. One cycle of the curve. One period of the function is one cycle of the curve. You go from one point to the equivalent point somewhere else. Okay. Sort of nitpicky there. Number 2. What's this about? Go nitpicky too. The blank of a sine or cosine curve represents half the distance between the maximum and minimum values of the function. Amplitude, very good. Number 3. For the function y is equal to a sine bx minus c, c over b represents the blank blank of one cycle of the graph of the function. What? Phase shift, exactly. Okay? Or horizontal shift, they may call it. Number 4. For the function y is equal to d plus a cosine bx minus c, d represents a blank blank of this basic curve. Vertical shift, very good. Okay, homework exercises, which I think I've given you most of these before, but here I'll do them again. Any of the odds 5 through 11, all those are at calcchat.com, 7's at CalcView. Any of the odds 13 to 23, I would say 13 to 19, and then 21 and or 23. Do some with just the formula, some with the graphs. And all those are at CalcChat, none of them are at CalcView. Any of the odds 25 to 29, they're all 3 at CalcChat, the 27's at CalcView. Any of the odds 31 to 51, they're all at CalcChat, 49's at CalcView. Any of the odds 53 to 57, all 3 of those are at CalcChat, 55's at CalcView. Any of the odds 59 to 63, they're all at CalcChat, none of them are at CalcView. Do either 65 or 67, they're both at CalcChat, but only 65's at CalcView. Do either 69 or 71, they're both at CalcChat, but 71's at CalcView. Do 73, it's only at CalcChat, they don't have it at CalcView. And then do any of the either 75 or 77, they're both at CalcChat, but only 75's at CalcView. Then your applied problems, any of the odds 79 through 85. Okay? Some of those are, fairly similar to the one we just did. Some of them are a little bit different, but they're applied problems. Oh man. Do either, on the exploration, the true false, it's good to think through either 87 or 89 or both. Again, I think they're at CalcChat. They're not at CalcView, I know. Then conjecture, 91, that would be sort of interesting to think about. 93, you can think about that. If you want to sort of find the paper topic there, you might, but that looks pretty esoteric. And then number 95, if you want to take a look there, you can as well. Now, there is a project at the bottom, meteorology, based on some precipitation in Honolulu, Hawaii. If that's something that would be interesting to you as a paper topic, you might want to look there. But that's completely up to you. All right, any questions on 4.5? Why is this not advanced? Oh, I know. I already advanced. So let's move on to 4.6. Now, I may have to pause just a moment here and go clear my head, for suddenly I've just gotten all congested. So while that's trying to come up, all right, let's go from the current slide. It's coming in slowly here. Still, in Chapter 4, trigonometry, the measurement of triangles, that's what that stands for. It's like crazy. The last section, we did graphs of sines and cosines. This section, we'll be doing graphs of your other 4 trigonometric functions. Okay? The first 2 of the, well, can anyone tell me conceptually a difference between sine and cosine functions and the others? Is there anything philosophically or somehow different between these functions? Sine and cosine functions are smooth, continuous functions everywhere. Anyone remember anything different about the other 4? Yes, they have vertical asymptotes because they're not defined, because the other 3, sine and cosine, or sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. And guess what? Hypotenuses are never 0. You're absolutely right. On the unit circle or any circle, if you got a triangle there, you have a hypotenuse, right? That's non-zero. Hypotenuse is never 0. But the other functions are ratios of those, and both sine and cosine are zeros at certain points. So everywhere that the sine is 0, then your cotangent and your cosecant not defined. Everywhere that the cosine is 0, the tangent and the secant are not defined. They have those vertical asymptotes. So that's why they sort of separate them out in that sense. Okay? So we're anticipating some vertical asymptotes coming up here. Other things that we anticipate, of course, if they're going to vertical asymptote, that means the function's going to infinity, either positive or negative, somewhere or another. That's what a vertical asymptote is. Okay, so they'll only be defined for certain portions of the domain. Let's take a look at those. So we'll sketch the graphs of the tangent functions first, and then cotangent functions. And as you might guess, they're sort of related to each other. Okay? Not as closely as sine and cosine. Sine starts at 0 and does like this. Cosine starts at 1 and does like this. But they look almost identical except from where they start. Tangent and cotangent look similar but not nearly identical. Okay? We'll see that. Then we'll sketch the graphs of secant and cosecant functions. Now, which you reckon would be the most difficult to do? These or those? Just hazard a guess. Tangent, cotangent, secant, cosecant. Yeah, they sound like they should be. But once you see how they do them, have a piece of cake. Okay? So we'll see. And then we'll sketch the graphs of some damped, be sure you put your P in there, trigonometric functions. Okay? So, I know you've been calling them otherwise, but let's not. Okay? So let's start with the graph of the tangent function. I don't know if you recall this, but the tangent function is an odd function. That is, tangent of minus x is minus tangent of x. Okay? In other words, whatever tangent is doing over here, it does the opposite on the other side of 0. Okay? Tangent of minus x is the opposite of tangent x. Consequently, the graph of y is equal to tangent x is symmetric about the origin. Okay? You also know from the identity that sine x is equal, tangent x is sine over cosine. Tangent is not defined every place that cosine is equal to 0. Not defined. You can't have it there. Now, where is that true? Cosine is 0 at your half pies. Half pi, 3 has pi, 5 has pi, 7 has pi, negative half pi, negative 3 has pi, negative 5 has pi. Every half pi you've got is not defined. So, as you said, you're going to have vertical asymptotes. Every half pi. Oh, well, every pi on the half pies. Okay. Now, they also it hurts like crazy. They say that pi is approximately 1.5708. Okay, half of 3.1416. Okay, so yeah, that's your half pies. So why they have this much detail in the table, I'm not sure. But like they just said, it's 1.5706. So they take it up to 1.57 and negative 1.57. Plug in those values, that's going way negative here, way positive there. Of course, it's undefined vertical asymptotes at those two. Now, they also backed off a little bit from that, from negative 1.57 and 1.57 to 1.5, negative 1.5. You see just that little bit of difference there got you down from negative 1200 to negative 14. So it's a really rapid change, real close to pi halves. Here is the point that really is of interest. I hope you remember this. At your quarter pies, remember it's square root. The sine is square root of 2 over 2. Tangent is cosine is square root of 2 over 2. So tangent is 1. So the pi fourths, you're at plus 1, right at 0, and minus pi fourths, you're at minus 1. That's your key point. Okay? The book doesn't make as big a deal about it, but that to me is how I go about graphing my tangent function. I know at my half pi's, okay, you're going to have vertical asymptote. I know at the 0, you're going to be at 0. And at the quarter pi, you're going to be minus 1 plus 1. Those 3 points enable you to do it. So it's indicated in the table, the tangent increases without bound as it approaches pi halves, decreases without bound from the left, decreases without bound as it approaches negative pi halves from the right. Okay? Now, here's then how it looks. At that vertical asymptote, it doesn't just approach infinity. It flips infinity. It's going to positive infinity here, never, of course, gets there, but then comes up from negative infinity here. So every vertical asymptote, now that's not true for all vertical asymptotes, but it is for tangent, and later we'll see cotangent as well. You completely flip to a different infinity, as you cross that vertical asymptote. Okay? Now, what is another thing you notice about this? This is a graph from negative pi halves to pi halves. Here it's minus 1, negative pi fourths, plus 1, negative pi half, positive pi half, pi fourths, I can't talk, okay? Plus 1 there, and then that's the tangent function does that. What's the period? So sine and cosine. Remember that? What's the period for sine and cosine? 2 pi.
2 pi over b.
Okay, yeah, if you had a b in there. But just plain sine and cosine without any b's in it, it would be 2 pi, just 2 pi. Well, for tangent and cotangent, they're the only two, their period's only pi. Here's part of the reason. If you remember, all students take calculus, right? All functions are positive in the first quadrant. Sine is positive in the second quadrant. Tangent is positive down here. Cosine is positive over here. And then the reciprocals are there too. Cosecant, cotangent, and secant are positive. So if you think about it, a sine is positive, positive, negative, negative. That's one cycle. Positive, positive, negative, negative. Cosine would be positive, negative, negative, positive. Okay? Starting positive, going negative, negative, and then positive again. So it has to take the full circle to go through one cycle. Okay? The tangent is positive, negative, positive, negative, positive, negative. Its cycle is pi. Not 2 pi, but pi. It goes through its complete cycle in pi. So its period is only pi. The same will be true for cosine. Cotangent. Okay. Your secant and cosecant go back to being 2 pi again. We'll get there later. So, what's your domain for your tangent function? Every value from minus infinity to all real numbers except your half pi's. Every half pi. So all x is not equal to pi halves plus n pi. Notice it's not 2n pi here because the period is pi. Range, again, different from sine and cosine. Sine and cosine, what's its range? Plus or minus 1, exactly. Or if you have an amplitude, plus or minus a. Unless you have a phase shift. We won't get into that. But tangent and cotangent, negative infinity, positive infinity. Okay? The only two that are like that. Okay? Yes? There's a question. Oh. Now, vertical asymptotes, where your domain is not. I don't know if y'all are Winnie the Pooh fans, but one of the stories there was where the woozle wasn't. Okay? One of my favorite stories of all time. But where is your vertical asymptote? Where the domain wasn't. Okay? Where you didn't have a domain defined, those are your vertical asymptotes. Okay? Pi halves plus your n pi. n pi, not 2n pi, because period is just pi. And it's symmetric about the origin. What's another way of saying that? Odd function, exactly, symmetric about the origin. That means the same thing. All right, good deal. So, not that hard to graph, as you might guess. Moreover, because the period of the tangent function is pi, the vertical asymptotes also occur at every n pi multiple, which we already talked about, where n is any integer. Whereas sine and cosine repeat every 2n pi, tangent and cotangent repeat every n pi. The domain of the tangent function is the set of all real numbers other than your half pi's, or I(m) plus n pi, or n to any integer. Okay. Range set of all real numbers. Same thing we said on the last slide, only we're writing them out here. Sketching the graph of y is equal to, okay, now they've thrown in all the other things here for you. All but one. They didn't do the d. If you're sketching this one, a tangent bx minus c. Now, of course, I like to take the b on the outside, make it b times what they call x minus c over b. Why not take it on the outside? Just call that c. That then becomes your phase shift the way they do it. C over b becomes your phase shift. So why not factor it out and then let c be your phase shift? What you do in physics. Sketching the graph of that is similar to sketching the graph of a sine b minus c, in that you locate the key points that identify the intercepts and asymptotes. So they say it's similar, except you intercepts and asymptotes. The sine doesn't have any asymptotes, so, but I know what they're talking about, and they're saying it okay. What does A stand for here? What's it related to? Amplitude. What would you say the amplitude of a tangent function would be? Yeah, it's infinity in both directions. So it doesn't have an amplitude. So why even mess with the A here? What does that tell you? Well, if you go back here, remember your plus or minus ones here? If you had an A there, that would be plus or minus A. So even though it doesn't have an amplitude, A is still a nice parameter to notice, because that tells you where to put your quarter pies, or your quarter period. Okay, because the period is pi, that makes the quarter period a quarter pi, and that tells you where to put that. So the A in the regular thing, that's 1. But if you have A tangent something over the other, then you're going to plus or minus A. So it is a nice parameter, even though it doesn't stand for amplitude in cotangent or tangent or secant or cosecant. None of them have amplitudes, but they actually, you don't worry about them. We'll get to that later. Okay. Okay, the B though, how do you think what would be down here? Second, it related to the period, and the period was 2 pi over b. So guess what it'll relate to here? Yeah, it'll be pi over b. The period will be pi over b. And the phase shift here, which they call c over b, if you factored out the b, it would just be the term c. That's going to be phase shift 2. That's a horizontal shift. That will be just like before. So, A's are still important. It's an amplitude here. It's where your quarter pies are here. Okay? The B relates to the period just like before, except this is 2 pi over B is the period. Here is pi over B is the period. And the phase shift exactly the same. Okay. All right. So here's how okay. Now you can do this either way you want to. The way they do it is that when they have this form here, the b minus bx minus c, that goes the left-hand asymptote is going to be at minus pi halves, the right-hand asymptote at pi halves. So that's what they say. You can set these up and figure out where these are going to be. Okay? So bx minus c is either minus pi halves, that'll be this asymptote, or bx minus c is pi halves, which is that. If that's the way you want to do it. It's pretty simple just to pick them out and go with it. But we'll get there. The midpoint between two consecutive vertical asymptotes has to be the x-intercept. Has to be, because it's going negative infinity there, positive infinity there, midpoint's going to be at 0. Okay? So that's an easy way to do that. Frankly, that's how I begin. This is how I do it. I start with the intercepts, and we know where that's going to be. Where sine is equal to 0, that's where tangent is equal to 0, because sine over cosine, right? So start with where that is, and then do half a period this way, half a period that way, put your vertical asymptotes in, and you don't have to worry with this anymore. You know, to me, that's a lot simpler than the way they do it. But if you like this, go for it. It works. The period of the function y is equal to a tangent bx minus c is the distance between two consecutive vertical asymptotes. Guess what? It's also the distance between two intercepts. So either way you want to look at it, asymptotes usually is what I think in terms of, and that will be pi over b. Not 2 pi over b, pi over b. That's what we're going to do. Okay. Amplitude of the tangent function not defined, so they sort of ignore the a. Don't ignore the a. That's going to be at your quarter periods. Okay? Plus or minus at the quarter periods. Okay? After plotting the asymptotes and the y-intercept, plot a few additional points. And guess what the easy one? Quarter periods. Minus a plus a. Okay? Why don't they say it? I don't know. Finally, sketch 1 or 2 additional cycles to the left and to the right. Stand up, sit down, fight, fight, fight. Okay. So let's do this one. Sketch the graph of y is equal to tangent x over 2. Now, I like to begin this just like I did for sine and cosine. Identify your parameters. What are those parameters? I don't know why this came up. Okay. Yeah. What are your parameters? A is equal to, it's as simple as A, B, C. Okay, remember? A is 1. B is help me. What would be your B? It's the coefficient for x. 1/2. How about C? 0. There is no C. And there's no D either, but they don't even mess with D's much here. Okay, you could, but they don't usually do it. All right, what does the A tell you? It's what? Yeah, that's where your quarter periods are going to be. Exactly. Okay, think of in periods rather than pies. In regular, it would be pi, but you know, this is going to be adjusted there. Your quarter periods are going to be. And that's going to be plus or minus 1 at the quarter periods. Okay? What will B relate to? What will B relate to? The period. And how does it relate to the period? Pi over B. And that would be pi over, what do we say B was? 1/2, which will then be what? 2 pi. So here we go back to the period being 2 pi again. So that's only because the B is not 1. Okay, it's 1/2. Okay, so there's your period. And then what do we usually do once we get the period? Divide by 4, okay? Your quarter period would then be 2 pi divided by 4 would be pi halves. And I call this your interval. That's what I like to call it. That's the interval I'm going to put on my x-axis. Okay? And then you have no phase shift, so you know where to start. Okay, let's get the graph going here. Since there's no phase shift, where's the tangent going to begin? At 0, just like the sine does. Okay, so it'll be at 0. Okay, and let's just tick off a few points here. 1, 2, 3, 4, 5, 6, negative 1, 2, 3, 4, 5. Okay, something like that. I didn't space them very well, did I? Very lousy, in fact. Okay, now these are going to be at your quarter periods. That's going to be pi halves, pi, 2 pi, and 3 pi. I just don't want to put all those halves in there. Minus pi halves, minus pi, minus 2 pi, and out there somewhere is minus 3 pi. Okay, those are your intervals, or your quarter periods. So there's your 0, your intercept. I really space these really poorly. Okay, your quarter periods, minus pi halves and pi halves, that's where your intervals are. Okay, that's going to be what value? Minus 1 and 1. So you'll put a minus, so let's go and just tick off a 1, 2, 3, 4, negative 1, 2, 3, 4. Okay, so down here it's going to be at negative 1, up here it's going to be at plus 1. Now what's going to be at half a interval from your, half a period from your intercept? Okay, 1 period away, that would be 2 pi away, you're going to have another intercept and another intercept. Whoa. Yeah. Okay, and what's halfway between your intercepts for tangent and cotangent? Your vertical asymptote. Halfway in between every one of those, a vertical asymptote. Oops. I kind of like to do vertical asymptotes in red, if I can get red to come up. Okay, that means you can't touch there. Stay away. Okay. I can get that one in. I can't get the other one in because it didn't go far enough. Okay, I'm really off kilter here. Okay, let's go back to dark. So, where are we going here? You go up to plus 1 to positive infinity, down to minus 1 and minus infinity. Up to plus 1 and positive infinity, down to minus 1, and you're heading toward negative infinity. Up to plus 1 and positive infinity, down to minus 1 and negative infinity. That's how it looks. Now, for those who so fondly remember your translations back in Math 112, you had shifts, and then you had shifts for rigid translation. That's when you add or subtract. And then your non-rigid translations were your shrinks and your stretches. In this case, we have a horizontal stretch by 2. Remember, anything you do to an x, and that's why before the vertical asymptotes would have been at the half pi's, now they're at the full pi's, because your period changed because of that dividing by your b. So now you're going like this. So there's your graphs of those functions. And helpful to use the quarter periods to get your plus a and minus a. In this case, I'm sorry, minus a plus a, minus 1 and plus a. Does that kind of make sense? All right, good deal. That was example 1, and you see it in your text. So I'm going to erase my chicken scratch, and we'll take a look and see how they do it. Now they start by solving these equations. To me, it's so much easier to start with your midpoint, and then half a period away, you got vertical asymptotes. But if you like doing it this way, do it this way. It's fine, works perfectly fine, okay? This gives you x equal minus pi and x equal positive pi for your two consecutive vertical asymptotes, okay? And then 2 pi away from each of them, because your period is 2 pi, that's where you would go, okay? Between those two vertical asymptotes, then you put right smack in between is your intercept. To me, let's start at the intercept and go half a period this way, half a period that way, you get your vertical asymptote. Either way you want to do it, it works fine. And then a quarter period away from your intercept is your plus A on the left-hand side of your minus A. Okay. Those are the key points. Get those plotted. Of course, the vertical asymptotes aren't points, but they're locations. And then just plot through the other 3 points. Approach infinity, one side or the other at the others. Make sense? All right, so here's how the graph goes. Differences in their approach. Their approach, they do the vertical asymptotes first, then do the midpoint, then do the other points. I like to do midpoint, the intercept first, put your vertical asymptote half period to the left, half period to the right, and then halfway between those two, put your plus or minus A. And it's just pretty easy to plot that way. Okay? And it uses the ABC just like we did before. Okay? So to me, the transition is pretty smooth there. All right. They skipped example 2. Shame on them. Okay, let's do example 2. Sketch the graph of y is equal to -3 tangent 2x. Now, where do I suggest that you start your looking? Your parameters. What are your parameters? They're as simple as A. What's your A? -3. Next. B. 2. C. Zero. There is no C there. Okay? What does, now the A is going to relate to your locations at your quarter periods. Okay? So we won't go there yet, but that's what it'll relate to. The B, though, we do need to deal with. What does B relate to? And what's the period? Pi over B, which in this case is 2. Okay, there's your period, the full period. And what do we usually do with that? Divide by 4. So your intervals then would be divide that by 4. Pi over 8, absolutely. Okay, those are going to be your intervals. So and that basically is kind of all you need to do your graphs. So let's tick off a few points. 1, 2, 3, 4, 5, 6, 7. Okay, -1, 2, 3, 4, 5, 6, 7. And let's go up 1, 2, 3, 4, 5, 6. Down 1, 2, 3, 4. Okay, something like that. Okay. Now, since you have no phase shift, your C is 0, no phase shift, where is tangent going to begin? At the origin, 0, 0. Okay? Now, we want to go half a period to the right and half a period to the left. That will give you your vertical asymptotes. And if your period's pi halves, what's half of that? Oh, I should have put the intervals in. Let me do those. Pi eighths, pi fourths, pi halves, I skipped one, and then this would be, I don't do it, I'll just put 3/4 pi. 3/2 pi. No, 3/4 pi. I didn't mean to do that, but it need to put something out there. This will be minus pi eighths, minus pi quarters, minus pi halves, and then this will be minus 3/4 pi. Oh, that's it. Okay. And remembering that your period is pi halves, so that'll be from minus pi fourths to positive pi fourths, right? Half a period on either side of the origin, right? So what's going to be there? Hint, I'm changing colors. Vertical asymptotes. There and there. But then also there and there. Okay, those are vertical asymptotes every pi halves unit. Because from minus pi fourths to pi fourths, that's pi halves. From pi fourths to 3/4 pi, that's pi halves. You know, so every one of those intervals is pi halves. Okay? Let's go back to my dark color. And what's in between all the vertical asymptotes? Your intercepts again. So those are at your half pi's in this case. Now, what's in between your intercepts and your asymptote? That midpoint there, your quarter periods are going to be your plus or minus A. Now, what's a little different here, A is -3, so that means going to the right, this will go down to 3. If that had been a +1, it would have been going up to 1, or a +2, it would have been up to 2, or +1/2, it would have been up 1/2. This is a minus, so it's going down. So on the other side, that's going up 3. Okay? And you can put those in every place. +3 here, -3 there. +3 here, a -3 over here, a +3 right here, and a -3 down here. Okay? All right. So this is coming down from here like this. Down from here like that. Obviously don't hit my points very well. Whoops. I'm doing pretty poorly, in fact. Okay. And this one would be heading down this way. Okay. See how it looks?
Yes.
Okay. And again, the key points are, know where you begin, your intercepts. Most of the time, tangent. If there's no phase shift, you begin at origin. Okay. Then a half a period on right and left, those are going to be vertical asymptotes. And a full period away on either side of that, another vertical asymptote. And between your vertical asymptotes, again, your intercepts. And then between your intercepts, then your plus A and minus A. In this case, since A was -3, you do the minus A down here, plus A. Okay. Negative value down there. Don't tell me. Oh my goodness, how did it happen?
Yeah, it's like 3 minutes.
What's that?
That says like 3 minutes time.
Yeah, okay, sorry. No extra charge, though. Don't worry about it. Okay. So we'll pick up next time with graph of the cotangent function, which will be right there. Okay. Homework exercises. Don't leave home without them, okay? You can do any of the odds. In fact, I would do all of 9 through 14. The odds will have answers in the back and at calcview.com. But whoa. Yeah, I don't think we've gone far enough to do those. I think you skip those first ones. I think you can do 15, possibly 19, possibly 29, 39, 43, ooh, that was interesting, and possibly 47. Okay, we'll pick up and do most of the rest of them after that. Hey.
emailed you?
Yes.
Okay, so I did, like,
Okay.
right here.
Okay. Good
And
deal.
I didn't know
Yeah.
if you was gonna have a recommendation on file. I did.
What's
have a
that?
type of recommendation.
Oh,
You can-
okay. That'll be fine.
Okay, you can just,
Yeah. Did you send me this too?
I did.
Okay.
Because I can't send it to you.
Yeah. Well, yeah. That really. Did you send this to electronically also?
Yes, I sent all this electronically,
Okay.
but they won't.
But
be
yeah.
sent-
Yeah. This will be easy just to fill in.
Right.
This will be easy to do if I got your thing. I'll probably adjust it.
Okay. What else was I say? When can I?
Okay.
Because let me just explain this to you.
Yeah.
I was informed about this yesterday,
Right.
and it's due today.
Due today.
Right.
Okay.
So that's I'm saying if you want to just read it and have me type extra words that you want to say.
What I'll do is if you send me this,
Mhm.
I'll fill in this part. Okay,
Okay.
that's no problem. If you'll send me this, then I'll do in the extra words. For instance, I'll change this to. Oh, she's the one we send it to?
Right.
Oh, I see. I was thinking you had, okay. Yeah, if you'll just send this to me, then I will, I'll do this and I'll get it done. I'll send it back to her then.
Okay, you'll send all this to her?
Yeah, okay. I will, is she on this campus or
I
that
think
campus?
she's on Birmingham's campus, but I was told that if I did not see Miss Tracy, Dr. Tracy, to give it to Dr. Pruitt.
Okay. Well, what I'll do on my way home today, I'll go by the Birmingham campus.
Okay. Thank you
and
so
I'll
much.
drop it off.
Thank you.
So if you'll send me this electronically, I'll adjust it.
Yes,
And
sir.
then, because I don't want it to look like everybody else's.
Right.
Yeah.
Yes, sir. Thank you so much.
All right,
Dr.
glad to. Uh-huh.